So we're going to continue the topic of integrating to find the electric field due to what we call a continuous charge distribution. Ultimately, our thin rod or a wire, something along those lines, where there is charge distributed all along the length. Now, to start this, I want to actually ask you a conceptual question that I will bring up in just a minute. Be sure to pause and answer the question on your own, and then I will go through it and also continue this topic as part of that discussion. All right, so this question, what do you think the answer is? Okay, the correct answer here is E. So if we think of each of these little positive signs as individual point charges, because as we've mentioned in previous videos, that's what we're doing mathematically to calculate for the overall electric field. I won't write it as absolute value right now. But to find the overall electric field at a point, we have been adding, summing, so integrating the effect and each charge has at that point. So here, this N charge on the left would be creating an electric field. It won't be nearly as strong as, say, the one right here. That will be stronger, but it will also be in a different direction. If we look at the positive charges on this other side, that will be to the left and upwards. So ultimately, the three charges right here, their X components will cancel with the other three just to the other side. They both are creating positive Y components for the electric field, but the charges on the left are creating a positive X component, while the charges on the right are creating a negative X component. So those cancel out. But that doesn't mean there's no X component at all, because we now have all of these charges down here that don't have any charges on the other side to cancel with. And so these X components are going to add together. So overall, we'll end up with a positive X component of electric field and a positive Y component of electric field. Now, similar to the previous examples where we had to figure out how to write dq and r in terms of the same variables, that portion is going to still be similar to what we did before, but a big difference is going to be this r hat vector, this unit vector. And that's because the electric field, due to all of these different point charges, has a different direction. So that means r hat, the vector describing the direction, is going to change for all of them. And so that's what we're going to set up and talk about. Let me just draw a new picture representing that one that we were just looking at. So let's say this is our positive charges. I'm going to go ahead and just make that the x-axis like it was in the picture. One other thing I'm going to do is the point of interest, that point A that we were looking at. I'm going to put the y-axis right there, just for simplicity's sake. Because if you remember in the previous videos, when we wrote dq, we could say it was lambda dx or lambda dy, and then r was in terms of just x, how far from the origin. To keep that similarly the case, it makes it easier to just go ahead and put this y-axis going through the point of interest. So this dot I've drawn right here represents that point A. It is going to have some distance. I'm going to just call it lowercase a. So some distance up above this charge distribution. So this thin wire I've drawn represents our charge distribution lambda. I'm just going to say the left end is at some position x1. The right end of the rod is at some position x2. So I'm just going to solve this symbolically first. So I'm going to assume I know lambda, x1, x2, and a. As we already talked about with the figure before, we expect the overall electric field over here to have a positive x component and a positive y component. But we need to be able to show that by setting up the integral. So similar to before, we do need to write dq in terms of our variable. So let's think about our variable. Regardless of the situation we're integrating, we're considering our object as a bunch of point charges, because that's essentially what it is. They're much closer together than I'm drawing. Each of these point charges we're saying has an amount of charge dq on them. Because this thin wire or rod is along the x-axis, I'm going to say the length of this little point charge is dx. Now, I'm noticing in my equation I don't have r squared. I apologize for that. R, remember, is the straight line distance from the piece of charge we're talking about to the point where we're trying to find the electric field. This electric field points along that line. This is what we were calling dE before, the electric field created by that one piece of charge. If I think about another piece of charge, say this one right here, it also has charge dq, length dx. R is the straight line distance. R is different though, and the direction will also be different, but there will be an x and y component of this electric field. Now R, if we think of just this triangle right here, in my coordinate system, right here is my origin. So if I measure this way, that's a distance of x. It is on the negative side, but we can still just say it's an x value. This vertical side, which I've chosen to call A, is constant. So even if I go back and look at the first point charge I drew, and the first R I drew, this vertical side is the same. It's this horizontal side that is different. It is totally valid to say that R, that straight line distance using Pythagorean theorem, will be the square root of x squared plus y squared. Now, because I have labeled that vertical distance as A, meaning a specific value, plugging A in for y, because y is not changing, I can say that R is the square root of x squared plus a squared. R is changing. R is different for every piece of charge, but it's different because this horizontal distance is different. The vertical distance is not changing. So this is telling me that my variable is x. That is the variable that's changing as I look at all of these different pieces of charge. That x distance is changing. So to write dq in terms of dx, that's where lambda comes into play. The linear charge density can always be written as the total charge over the total length, but it can also be written as the charge on this little point charge, we're calling that dq, divided by the length of this point charge, which we're calling dx because it's on the x-axis. So dq is going to equal lambda dx. Excuse me. So in our electric field equation, so far we have dq and we have r. So far we can say E is k lambda dx over this r squared. Now r hat we still need to consider, because we have to account for the direction and how the direction is changing as we look at all these different pieces of charge. So coming back to the picture, I drew first this leftmost circle I drew. I'm going to call that number 1. This middle one I drew number 2. We have to account for the direction of every single point in between and beyond 1 and 2. I just wanted to draw 2 points that we could see, obviously, that R was different. Now, the direction of their fields up here that we drew are different as well. They point at different angles. So if I was just to draw one of them, a little bit bigger to see better, DE represents the magnitude, which is what we have written down here right now. But it has an X component and a Y component. Those X and Y components are changing both because DE, the magnitude, is changing, but also because this angle in here is changing. Right? If we come back to this first dot I drew, the angle's shallower than this newer angle here. And since the electric field points directly away, the angle it makes with the horizontal up there at that point is the same as the angle it makes with the charged rod and R down below. So this X component we would calculate by having the magnitude, and then we would take times the cosine of theta, and that would be our X component. I was drawing the I hat to finish the vector. I'll do that in a sec as we write it out. For the Y component, we would take the magnitude and multiply by the sine of that angle. But again, this angle's changing. And so we want to get this in terms of the same variable. Right now, we have this dx, meaning we are integrating with x being the only variable. Nothing else changing. But theta is changing. I'll show you how to do that. So first off, though, I want to write this out in terms of vectors so you can see what I'm going to do. So the vector representing the electric field due to just one single point charge will be the magnitude times the cosine of theta for the x component the magnitude times the sine of theta to get the y component. The magnitude's the same either way, so I can factor that part out. So again, what I boxed right here represents the magnitude of this electric field. This, I'll box it, is r hat. That represents the unit vector that describes the direction of the electric field at that specific location. Now, I can't plug it in yet into my equation because I need to somehow write this in terms of x's and constants, because I'm going to integrate with x as my variable. So I want to come back to the original picture. Let me choose a different color. So either one of these, if I was talking about this second point, again, the theta down here is the same as the angle that the electric field vector makes with the horizontal. So if we think about this triangle, just in terms of dimensions, this side is x, this side is a, and the hypotenuse is r. So in that triangle, the cosine of theta is going to be x over a. That's so not true. Good grief. Sorry. Cosine of theta is adjacent over hypotenuse, r. And we know r is the square root of x squared plus a squared. So this is the cosine of theta. We're going to put this in for cosine theta. Similarly, our equation has sine of theta. I'll write that on the bottom. Sine of theta. So sine is the opposite side over the hypotenuse. So a over the square root of x squared plus a squared. This is what we're going to put in for sine of theta. I know it looks big and crazy, but now if we go to plug things in, I'm just going to rewrite what I have here. So the magnitude portion, and yes, I do realize the square root of x squared plus a squared, quantity squared. The square and the square root cancel. But I'm leaving it that way for a reason. So the magnitude times, now I'm plugging in what represents r hat, the direction. So the x component was the cosine of our angle, which we are just writing in terms of dimensions because we know the shared angle. And then the sine of theta for the y component. We will need limits of integration, which again describe where the charge is distributed. So the 2 points the charge is distributed between. So that's what I labeled originally. X1 was the left end of the rod. X2 is the right end of the rod. The left end is the lower limit. The X2 is the right end, the upper limit. So we end up actually with two integrals here. We have to factor the magnitude in to the x component. So k lambda x dx over, in the denominator I have the square root of x squared plus a squared, and that is squared. And I'm multiplying that by the quantity of x squared plus a squared, or the square root of that. Since they are the same quantity, x squared plus a squared, the power, I essentially have the square root I could have written as 1/2 is the square root power. So I have 2/2 here, I have 1/2 here. So that is leaving me with this quantity of x squared plus a squared to the 3/2. That's our x component. The limits of integration are from the left end of the rod to the right end of the rod. So whatever our variable x is changing between, then I need to take the same magnitude and multiply it over through to the y component. Let me write my a in front of my dx. Same limits because our variable is x. We're still saying the charge lies between x1 and x2. That's what the limits are essentially telling us is, hey, the charge exists between these 2 points. So we ultimately end up with 2 integrals to solve. This one will give us the overall x component of the electric field. This one gives us the overall y component of the electric field. Okay. As far as the integral that needs to be done for the x component, if lambda is uniform, then I can pull out not only k, but I can pull out lambda. I can pull the I hat in front as well if I'd like. And I'm left with x dx over this quantity of x squared plus a squared to the 3/2. For the y component, again, I can pull out the constant k, I can pull out the lambda, I can pull out the a, because remember, a meant that vertical distance from the charge up to the point we're trying to find the field at. This integral ends up being dx over x squared plus a squared to the 3/2. Okay, it turns out that these are common integrals to be found in electricity and magnetism. Currently, if you turn to the back page of the test notes, you will see these equations. And I'm going to go copy them out. I'll bring them in just a sec. They're going to appear magically. All right, so probably a bit of jump on the screen. Sorry about that. We have 3 integrals listed here. All 3 of these are very common, and so we just use an integral table, meaning a known solution for those. So for the x component, I'm going to go ahead and write down my constants, but now I'm going to look for this integral. This integral matches this third one on the list. That means the solution to this integral is -1 over the square root of x squared plus a squared. The sign in here is based off of the sign that was in the integral. Since we have x squared plus a squared, we use x squared plus a squared. Now we would still need to evaluate this integral between our 2 limits. And this would give us the overall x component of the electric field. Similarly, for the y component, we have our constants, and then we look for this integral. This one matches the middle. integral. So our result, again, the plus or minus signs are based off of what we have in the integral. We have a plus. So we will have plus x in the numerator. You can write the plus if you want. I don't typically do that. Square root of the quantity of x squared plus a squared. And this will need to be evaluated between points x1 and x2 in order to then have the final answer. So don't stress the results of those integrals because those two are here. We just need to make sure we can get to the correct setup in order to choose which one we end up with. So from here, it would just be a matter of plugging in the upper limit and then minus plugging in the lower limit, and we would have the overall electric field at that, if you need a reminder, that point up here, some distance A from the rod. The general process of setting these up is the same. We want to find our dq. We need to write that in terms of lambda and dx or dy, something along those lines. R, the straight line distance from any one point to where we're trying to find, so the charge, 1 point charge, and where we're trying to find the electric field, which keep in mind that has been varying in every situation so far. The big difference here is when we have the point of interest that's not along the axis of the line of charge, the direction is going to be different for each point charge as well. And that's what we had to add in. And of course, it made it a lot more complex to figure out the sine of theta, cosine theta, factor it all through, all of that. So I'm going to do an example problem in the next video, and then we'll start looking at other charged objects as well.